So our main function about the implementation of the PVs and the operation algorithm is in the script daily simulation PV. So what's the idea here? So first we load the feeder data, so the data and configuration of the network and active and reactive power of the loads. After that, these are some variables needed for the process. And as it was said in the modification paper, we add 60 PVs per phase. So I just took a data sample out of the feeder loads, and if we take a look at the feeder loads, so let's see what are the feeder loads. So the feeder loads structure is none other than the loads in the system. So out of those nodes, which have some loads, we take 60 nodes to add the PVs. How to add the PVs? So first of all, we need to determine the nodes at which we will install PVs. So that's this part of the code. So that this is nothing technical. That's just randomizing the locations of the PVs in the network. And after generating the PV nodes, we need to generate the PV powers. Here, I took that the base power of the PV is the power of the maximal consumer in the network. So the power of the PV of the PVs installed in the phase A is equal to the power of the maximal load in the system times an uniformly distributed number from 1 to 2 of the length of the PV node. So we just generate an array with the length of 60 with which elements are numbers from 1 to 2 times the load of the power of the maximum load in the system. So after that, we do that for all 3 phases, and we just we just plot the penetration of the PVs in the system. After that, we choose the control nodes. So in the paper you sent me, it said that we should choose 3 nodes. To control. However, I think that's a bad idea because the network has 123 nodes. So you can't control the voltages in the system and control the reactive power in the system just by using 3 nodes out of 123 nodes. So that is why I've decided to use 15 control PVs. That's around 10% of the nodes in the system. And if you look at the paper you sent me, they use 1 control node for the network of 13 nodes. So that's also around 10%. So I think my observation and the choosing of the 15 control nodes is optimal. Increasing the number of control nodes improves the voltage profile in the network. So more PVs which we are able to control mean better flexibility in the system, and we can operate and we can control the voltages better. So the maximum reactive power of the PVs is said to be given for the maximum power of the PV active and times the sinus of the angle, which cosinus is 0.91. So 0.91 is given as the threshold power factor in the paper. So it's somewhere in the paper. After doing that, we just choose the pilot nodes. In our case, it also said that we should choose 3 nodes, three pilot buses. But I chose 5 pilot buses because more pilot buses means the better voltages in the system. So the overall number of variables is 45 because we have 15 control nodes in each system, in each phase. So this is the data we use to initiate the optimization process. Fitness is the fitness function, which we'll take a look later. These are just some equality and inequality constraints which are not needed. And non-LCON is nonlinear constraints, which concern the voltages in the system, and the voltages in the system should be in the area of 0.95 to 1.05. These are just the values required for the optimization function. Okay. Now we get the data on the daily load profile. So what is the function load curve? So the function load curve consists out of real-time data. So this is data from the real time about loads in the system. And if we run this function, we will get the daily load profile. So this is how the loads in the system change during the day. So the load for an interval, let's say the load at 5 hours will be the load which is given in the system. So let's say 10 kilowatts times 0.65. So this is how the loads change in the system. And after the loads in the system, we need to know how the solar, how the production of the PVs changes during the day. For that, we use the solar curve. And if we run, this is how the production of the solar power plant changes during the day. We can see that the peak production of the PVs is at around 14 or 2 p.m. Okay, so after calling that, we've initiated, calling both of these functions, we've initiated all the data required for the load flow simulation. This is just initializing the vectors for the power losses in the system, voltages of phase A, voltages of phase B, and voltages of phase C. These are the initial maximum reactive power for the PVs of phase A, B, and C. This is how much reactive power can the PV output for the initial case for if the production of the PV is maximum. However, the production of the PVs changes during the day. At a given interval or at a given time t, the value of reactive power which PV can inject is given using these equations. So we scale the values of the maximum reactive power in the system. Let's take a look at the main loop of the process. First, we go through the interval time. Time, as we can see here, is the 24-hour period, and for a certain given time t, the loads in the system can be obtained by scaling the loads with the load scaling factor, and the production of the PVs can be obtained by scaling the PV power or the PV capacity with the solar scaling coefficient. Like I said earlier, we need to also scale the maximum production of the reactive power production of the PVs, and this is just a vector of maximum reactive power production of the PVs, which is needed to run the fitness function. What does this optimization? What does this algorithm do? It goes through the array time, and for every time increment in the vector time, it runs the load flow. So here is running the load flow. So this is using the function three-phase load flow I already sent you, but it needs some modifications. So the modifications are to the feeder. Why modifications to the feeder? First, we need to scale the loads in the system. So we just scale the loads in the system in this step. So it's in this step, we just scale the loads in the system. In the step earlier, we determine the optimal reactive power output, so that during the interval tau, or during the interval t, all the constraints are satisfied. So the objective function, which consists out of these three objectives given in the paper, so f1, f2, and f3, is minimized using in this case I use def min con. The reason I use def min con is that it's much faster than the PSO. So the particle swarm optimization is also implemented, and you can just comment this part and uncomment this part to run it. So you can see also that it's implemented here in the files. So where is it? So it's PSO. So it's implemented completely with a large number of different functions. However, the PSO is much slower than the fmin-con optimization. So if I were you, I would use fmin-con, because fmin-con is a gradient-based method. So by nature, it is much faster than the meta-heuristic optimization algorithms like particle swarm optimization. So the algorithm works for both cases, but if I were you, I would rather use fmin-con because it's much faster, as you'll see. Okay, so after the algorithm minimizes the objective functions and returns the output of the reactive output of the PVs during the time t, we just add the PVs to the loads in the system. So we just subtract the production of the PVs from the reactive loads in the system, and we run the three-phase load flow. And that is done for every interval tau, for every interval t. And after that, we have the load flow for a full day with the optimized results. So after that, we just plot the results. So we plot the phase voltages in the system, and we plot the voltages of the pilot buses over time, and plot the changes of the voltages on the generator buses over time. After that, we just save the PV data and the data on control and pilot nodes, so we can maybe use it later. So the important thing to notice is that here I'm using random. So we're using random locations for the PVs and for the control nodes. So the alternative is to use some fixed nodes. So for example, let's say the nodes which PVs will be installed are nodes 3, 5, 7, 11, I don't know. But in this case, I left it random, so I can show that the procedure is working for all the cases. So it will definitely work on fixed cases. Okay, so let's just take a look at the fitness function. And the nonlinear constraints. So nonlinear constraints are, as proposed in the paper, we need to use the voltages of the load in the pilot buses and in the generator buses over time need to be between 0.95 and 1.05 in per unit system. So the nonlinear constraints implement so for a given interval t, we call this function, and using the data on the current time interval, so it just updates the loads and updates the power from the PVs and both active and reactive power, and it goes to the load flow methodology. And after that, we just have the voltages of the control buses and the voltages of the pilot buses. So we just make that a one vector, and we return C and C equality. So you can see that here we return C and C equality, and voltages minus 1.05 and minus V plus 9.95. So basically, what this means is that V has to be less or equal to 1.05, and V has to be higher or equal to 0.95. So this is what the function non-con implements. And now just let's take a look at the fitness function. So the fitness function takes the value of the reactive power in the system, and this reactive power in the system gained from the PVs is optimized using either PSO or using fmin-con or genetic algorithm or anything else. Every optimization algorithm can be used to obtain this Q. So we just add that Q and the production of the PVs to the feeder, so to the loads in the system. And after running the load flow, we determine the voltages in the whole network. And after determining the voltages in the whole network, we just need to calculate the fitness function. So the fitness function consists of three different functions. It's F1, F2, and F3. So the common way to solve multi-objective problems is to use Pareto optimization and fuzzy logic, as it was done in this paper. However, when implementing PSO or fmin-con, we need to use a different method. So because of that, we change the fitness. We change the objective functions F1, F2, and F3. So this part of the fitness function is not needed when running the PSO. So this value of the fitness function, or this part of the fitness function, is only for the Pareto and fuzzy logic. So it's for this implementation, and we don't need it for the PSO implementation. And it's the same with this part of the second objective function, while the third objective function also changes. So this stays the same, and we don't need delta VI. As you can see, the difference of voltage values between two computing steps. However, we don't have computing steps because of the optimization algorithm we are using, and because we are not using this algorithm, which was described here. So we don't need that part because we don't have steps between regulation. So if we go back to the fitness function, so we just calculate the objectives of F1, F2, and F3, and the fitness function is obtained as a linear combination of F1, F2, and F3. In our case, I gave more weight to the F1 and F3 functions because they concern the voltages in the system, and our goal is to optimize the voltages in the system, not so much the reactive power. So the second objective treats reactive power in the system, and the first and the third objective treat the voltages in the system. So let's just run the simulation now. This might take a while, so I will pause until the algorithm finishes. Okay, we're back. So it took the algorithm around 15 minutes to run. So, like I said, all the optimization algorithms are memory greedy in terms of memory and processing power, and they usually need a lot of time to work and to obtain the optimal solution. So, by, for example, lowering the number of maximum functional evaluations or by reducing the tolerance to constraints, or for that matter, reducing the number of variables, you can hasten the process of determining the optimal configuration of reactive power input into the network. The important thing to consider is that the algorithm does really fast during the off-peak hours, and the biggest problem comes during the peak production of the solar power plants, so during the peak production of the PVs, because that's when the voltages in the system are the highest. So it's very challenging to find the optimal configuration of PV injections into the network so that the voltage constraints are satisfied. So let's go through the results. So the first figure shows the PV powers or the active powers which the capacity of the PVs installed. So in phase A, phase B, and phase C. So nothing out of the ordinary there. You just have the bar showing the number of nodes. So it's connected to 60 nodes and capacity. So this capacity is shared to active and reactive power in terms of the production and in terms of time of the day. So the second figure shows the load profile I showed earlier. So this is how the load changes during the day. The second photo shows the changes of the production of the PVs in the system. And let's take a look at here, for example. So these are the voltages of phase A, voltages of the pilot nodes. And you can see that the voltages during the whole day are in the area of 0.95 to 1.05. So these are the 5 pilot nodes we've selected. So let's take a look at the other phases. This is for phase B. So the pilot nodes, the voltages of the pilot nodes of the phase B stay the same during the whole day. And it should be the same for phase C. Yeah, it's the same for the phase C. So the voltages of the whole network are within the predefined limits. So let's take a look at what happens with the generation nodes. So you can see also that it's the same with the PV nodes in the system, that the PV voltages of the PV nodes in the system stay within the required area, and it's the same for the PVs in other phases. Here, yeah, that's it. So the voltages in all the control nodes and the voltages in all the pilot nodes stay within the predefined limits. However, the important thing to notice is that we are controlling voltages in, let's say, around 40 or 30 nodes, and that the voltages in the system in the other nodes, because of large penetration of PVs, so this is a really large penetration of PVs. If you ask me, I would reduce the number of PVs to, let's say, I don't know, 40. So I think that would be much better than using 60 PVs. And you can see here that the voltages in other nodes, for example, this is during the peak production of the solar power plant. The voltages exceed, for example, 1.07. So it's not a large over voltage, but it's still larger than the predefined limits. However, the important thing to notice is that in the paper, they didn't treat the voltages of other nodes in the system at all. So they only show the voltages of the pilot buses and of the generator buses. They don't show the voltages of other nodes in the system. So it's a question whether they implemented it or not. The important thing to consider is that increasing the number of control PVs, so for example, if we say that we control 30 or 40 PVs per phase, then we can smooth out the voltage profile in the whole network. So we can control practically all the voltages in all the nodes in the system. So that would be it. Those are the results. It's the same for other phases. So the important thing is the idea behind the algorithm. So we just go through the time period during the day. So we just simulate the 24 hours. We just run the load flow, and before running the load flow, we determine the optimal reactive power output of the PVs in the system, and after that, we just run the load flow to test the results and to get the voltages and the power losses in the system during that.